Okay, organic chemistry 2341. This is the last section for chapter 8, alkenes and alkynes. Okay, so far we've looked at all the ones here on the right. We've done hydrohalogenation, hydration, halogenation, hydrohalogenation, hydroboration, oxymercurization, and we've done the osmium tetroxide. So let's do this last one with different oxidation reactions we can do with alkenes, and then we'll go into some reactions with alkynes. Okay, so the first thing we want to look at is the ozonolysis as an oxidative cleavage of alkenes. So the cool thing about the mechanism of the ozonolysis of alkenes is because the double bond, the pi bond, is the most active species there, it's going to attack that species first, and then it's going to further oxidize it down more. And so what we have here as our starting reagent is ozone. So the whole reason that works is the fact that ozone is a very reactive substrate right here and undergoes a 1,3 cycloaddition to create this 5-membered ring here. This 5-membered ring is not very stable and therefore will rearrange and to give us this 5-membered ring here. So if you think about this, this looks a little bit similar to a peroxide. But now notice that we have oxygens on we have 2 oxygens on each of the carbons. So that when we do a reduction to take it down to the byproducts, we end up with 2 different carbonyl products. So if we have an H on the double bond, we end up with an aldehyde. If we have 2 R's on the double bond, we'll end up with a ketone. Okay, so we can end up with a ketone, an aldehyde, or a mixture of the two, depending on how substituted the alkene is when we begin. Okay, so there's another way to cleave these alkenes, and that's with with permanganate. Permanganate is used right here, usually under basic conditions right here, and it'll again attack that double bond, either cis or trans double bonds, to create a carboxylic acid group that then can be protonated to give us acetic acid. So for example, if we were to do this reaction on this substituted alkene, we're going to break this bond right here. We're going to generate, because there's 2 substituents on the alkene here, we generate a ketone. And because there are hydrogens over here, those are going to further oxidize down and give us CO2. So if we have a terminal hydrogen, if we have a hydrogen on the alkene, we end up with a carboxylic acid. If we have a disubstituted alkene, we ended up with a ketone. And if we only have this methylene group here at the end, we'll end up with CO2. Okay, so if you have a terminal alkene, you end up losing some of your mass as CO2. However, this reaction is a lot easier to perform than ozone because ozone is a very toxic gas, and therefore you can actually do this without too many safety precautions in place. Okay, so we can use this to our advantage. If we have our double bond inside a ring, we can actually clip that ring to turn them into a long chain alkane. Okay, so in this case right here, we have a hydrogen on the alkene. So that means this portion here is going to oxidize down to a carboxylic acid, probably, or an aldehyde first. Okay, so then we also have this one right here is disubstituted, so it's going to turn into an L. It's going to turn into a ketone. So this right here is the functionality from this portion. Okay. The one with the hydrogen on it turns into the aldehyde here. And the one that's over here that is isolated, oops, didn't change color. The one here that's isolated, this part's going to go off as CO2, this is going to go off as formaldehyde. And then the other half is going to be this ketone here. Okay, so notice when we use the ozone, we end up with aldehydes as part of our product. In this case, a terminal aldehyde becomes formaldehyde. And if we used permanganate, we would get a different product. Okay, if we use permanganate, we would end up oxidizing these aldehydes down to carboxylic acids. So we have to choose our reagent based on what kind of product we want to end up with. Okay, so let's go on to our reactions with alkynes. So the first thing we can do is we can halogenate alkynes. And so if we just take one equivalent amount of an alkyne with one equivalent of a brominating agent, for example, bromine, we can add it across the double bond and it'll add across trans, right? Because we formed the bromonium cation intermediate, and then the bromine anion has to come in and attack from the other side, giving us the trans product. Okay, so if we had an additional equivalent of bromine, it will still react to give us the tetrabromoalkane compound. We can do the exact same thing with chlorine, and it's going to give us the same tetrachloroalkane product. Okay. So what if we, instead of adding a halogen across it, we added an acid across it, like HBr or HCl? So the first thing that's going to happen is we're going to get a trans addition with it, where we get the hydride at one side, the hydrogen at one side, and the acid at the other. And then now we have a difference, because if we had an R group here and an R group here, this is now the more substituted side, and this is the more hydrogenated side. Therefore, we're going to end up with a geminal dihalide, and we're going to have both hydrogens on the same side. So with the first addition, we have no specificity of where the hydrogen adds. But with the second addition, we do have specificity, and it does follow Markovnikov's rule. Okay, so just like we did with double bonds, we can do with that cleavage with triple bonds. And ozone is one of the better reagents we can do. It actually clips all the way through the triple bond, giving us 2 carboxylic acids. Because there were no other carbons available to us here, it over-oxidizes it all the way down to the carboxylic acid. And just like we had with the alkenes, it oxidizes it down to the carboxylic acids as well. Okay, so if we had a terminal alkyne right here, this will oxidize down to CO2, but we should generate the carboxylic acid from the other half. Okay,